Yes, sir.
Okay. And my voice quality is okay?
Yes, sir. Clear.
Okay. So slide number 1. We are now talking about stress. So if the question is, what is stress? Uh, the concept is stress at a point. Stress acts at a point. So if there is a point, there is stress on that particular point. So we know that what we do to calculate stress is we consider the load. We consider the load that is acting, total load P, and we consider the area on which the load is acting, say A, and we represent the stress as the average stress on the plane. So what we represent by sigma is P by A, and that is the average stress on the plane. So we assume that the stress is same on that plane. However, that need not necessarily be, it's an average, it's a general representation. However, stress may vary from point to point. So if you see actual variation from, if you consider the y-axis to be the stress axis, stress at a point P, so what may happen is the stress can vary, something like this. Up, down, up, with distance at every point, the stress can vary. And in average, you get that particular value. So stress at a particular point can be represented by the small amount of the part of the load acting on that point. And what we consider is, if there is a point, we consider a small area. We consider a small area around that point. So you can consider the area to be, say, dA, a very small area we are considering around that point. So actually, the stress at a point is the ratio of the load acting on that point divided by the small area that we consider around that point, and we write that limit dA tends to 0. Limit dA tends to 0. That means that small area is converging to the point P. So this actually gives the definition of stress at a particular point. This actually gives the definition of stress at a particular point, that is limit dA tends to 0, dP by dA, the small part of the load acting on that small area. And we consider that area is so small that it is limiting towards 0, 10 to 0. So on a plane, if we consider stress, it may not be the same, it may vary. We know that in dual phase steel, two kind of phases are there. One is ferrite, which is soft, and one is martensite, which is very hard. So if suppose on that particular plane there is ferrite and martensite, stress at a ferrite point and stress at a martensite point will not be the same, because ferrite is soft and it will deform, whereas martensite is hard and it will not deform. So the hard phase carries more load. So the stress in martensite can be higher. Similarly, in our bone, when our body is doing some work, our bone takes the majority of the load. So hard phase takes more load. So stress will be higher at those places. So this understanding is important, that stress varies from every point. and what we represent is the average stress considering a particular plane. Now again, coming to a particular point, say I am writing the point as point O indicated by the red spot, and we are considering a load or a stress acting on that particular point. And that point is a part of a body. That point belongs to a part of a body. So stress at that point inside a body can be represented by this diagram, by the parallelepiped that we are drawing. So having point O at the origin, you draw a parallelepiped around it. And how much stress that is acting at the point O can be represented in terms of stress components. So you can divide the stress at the point into stress components. So if the point belongs to a body, so now you can represent it that the stress that is acting sigma, actually you can divide it that there is a component acting this side, a component acting this side. There is a normal component. Similarly, there is a shear component. There is a normal component. There is a shear component. So in this way, you can represent the stress in terms of components. Because most simple way of loading we know is uniaxial tensile loading. Tensile loading is basically, we call it uniaxial when we do a tension test, because from the one direction we apply the stress. So this is the most simplest form of stress. This also we can represent in terms of certain component if we draw a point and a box around that point. So you will find there is a component this side, there is a component this side. But stress can be even more complex. Suppose consider a bridge. Why it is necessary to have understanding of different stress component? So there are pillars, and those pillars are applying a tension to keep the bridge straight. There are vehicles moving on the bridge which is applying a downward bending stress. There is wind blowing which is applying a stress on this direction. So there can be multiple components of stress. If you consider a complex state of stress, then actually a body is subjected to multiple stress components. And the best way to represent it is considering this parallelepiped, and the components are shown by acting on the major faces of the box. So these are the stress components. You see, suppose I consider the plane that is parallel to x direction. So I am redrawing the plane. So this is the plane that is parallel to x direction. This is the plane that is parallel to x direction. So the name of the plane is considered as x plane. I will consider it x plane. Here see the coordinates. I am writing coordinate as xyz. Similarly, you can also write coordinate as 1, 2, 3. In different books, you will find the coordinates are written in different way. So xyz and 1, 2, 3, there is no basic difference. So during the subsequent part of the lecture, you will find sometime I am using xyz, sometime 1, 2, 3 for the ease of representation. So please understand, x means axis number 1, y means axis number 2, and z means axis number 3. Now, what are the stresses acting on the x plane that is perpendicular to the x direction? You see sigma 1 1. 1 here is numerical number. Sigma 1 1 is the stress acting perpendicular to the x plane. On the other hand, sigma 1 2 and sigma 1 3 are acting on the x plane along direction 2 and along the direction 3 respectively. So sigma 1 1 is basically the normal stress. Sigma 1 2 and sigma 1 3 are basically the shear stress. Similarly, on the y plane, so this particular plane is called the y plane or plane number 2 because this is perpendicular to the y direction. So here we represent it as normal stress sigma 2 2, shear stress sigma 2 1 and sigma 2 3. You can also write sigma 1 1 as sigma xx. 1 mean x. So this can be written as sigma 1 1 means sigma xx. Sigma 2 2 means sigma yy. Sigma 1 2 means sigma xy. This is how it can be represented. Basically the same thing. So here, this is plane number Z or plane number 3. And on that, normal stress is sigma 3 3 and shear stress is sigma 3 1 acting along direction 1 and also sigma 3 2 acting along direction 2. So overall stress tensor is represented as sigma ij, and sigma ij can be represented by the 9 stress components: sigma 1 1, sigma 1 2, sigma 1 3, sigma 2 1, sigma 2 2, sigma 2 3, sigma 3 1, sigma 3 2 and sigma 3 3. You can also write them in xy form: sigma xx, sigma xy, sigma xz, sigma yx, yy, yz, and then sigma zx, zy, zz. So this is called the stress tensor, that whatever way you load a body or apply stress in whatever angle, whatever magnitude to a point in the body, it can be resolved into 9 components if you consider a box around it. And stress at a point can be represented by assuming that the box that you are considering is very small. So there are 9 components in stress in a body. Out of them, there are 3 normal components. The diagonals are basically the normal component, and the other terms are the shear components. And sigma ij is called stress tensor. Stress tensor. So in the form of a tensor notation, the stress components, tensor, T-E-N-S-O-R, can be represented. Now there is one aspect, that whether the body is stationary or the body is moving. A bridge, when we apply stress, it doesn't move from one location to the another location. So if you apply some force to something and it is moving, then stress doesn't generate inside that, because the force you are applying, it's going to translation. That means the body is changing its location. When a car is moving, you cannot say it will be deforming because it is not under stress. So whether something is under static equilibrium of force or dynamic equilibrium. Dynamic equilibrium means you are applying load and it is moving. In that case, the amount of stress will not be there. But when it is under static equilibrium, that means the stresses or the forces, basically, the forces acting in one direction has to be balanced. So when we are sitting in a chair, the chair is under a stress and it is under static equilibrium. But on the other hand, when we are pushing a car and it is moving, it is under dynamic equilibrium. So here we are interested about static equilibrium, which ultimately leads to deformation of a body. Now, for a body to be under static equilibrium, two conditions need to be satisfied. What is the first condition? The first condition is net force at any one of the direction has to be zero. So that is called force balance. Net force at any particular direction has to be zero. Now you can see that we are representing the dimensions of the body as dx, dy, and dz. The body has the dimension dx along x direction, dy along y direction, and dz along z direction. So now if we try to do the force balance, what will be the expression? Suppose I am considering direction 1 or x. X means 1. So along the direction 1, if we try to do force balance, what are the expression we were going to get? Sigma 1 1. Sigma 1 1 is basically acting on which plane? It is acting on x plane. What is the area of the plane? Dy dz. So the x plane has an area of dy dz. So sigma 1 1 dy dz is the force due to sigma 1 1 stress. Similarly, sigma 2 1 is acting on y plane, that is 2 plane, which has an area of dx dz. So sigma 2 1 dx dz plus sigma 3 1 dx dy, which is acting on the z plane, that is third plane. Net has to be 0. Now if we divide it by volume, then we will get this kind of a term for the stresses acting in dimension 1, direction 1. Sigma 1 1 dx by dx plus sigma 2 1 by dy plus sigma 3 1 by dz equal to 0. For a body to be under static equilibrium of forces, the body is not under dynamic equilibrium, but under static equilibrium of forces. Now, if we consider the force along direction 2 and along direction 3, two more such expressions will come. And in my PowerPoint presentation, I will show you those expressions. But you need to understand where from they are coming, and as I have already mentioned that. So, for static equilibrium to be maintained, force balance is the first criteria. What is the second criteria? Second criteria is the moment balance. That moment with respect to any major axis, axis 1, axis 2, axis 3, if you do a moment balance, then the net moment with respect to any major axis will be 0. Moment will be balanced. So considering that moment balance, you may do as a part of your exercise. The answer that we get is sigma ij equal to sigma ji. That means sigma 1 2 is equal to sigma 2 1. Similarly, we will get sigma 1 3 equal to sigma 3 1 and sigma 2 3 equal to sigma 2 1. That means these two terms are the same. These two terms are the same. and these two terms are the same. So shear stresses 1 2 2 1 same, 1 3 3 1 same, and 2 3 1 3 same. 2 3, yes, yeah, 2 3 2 3. These are the same. These are the same. So as a result, you will find that stress tensor is symmetrical tensor. Stress tensor is symmetrical tensor. So ultimately, how many independent stress tensor components are there? Stress components are there 6. Because if you know the 6 components, 3 normal and any 3 shear stress values, you can complete writing the tensor. And just one small additional information, when it is shear stress, often the symbol sigma is represented as tau, because tau we use to represent shear stress. You can write it sigma, but you can also use tau to distinguish between normal stress and shear stress. Normal stress is written as sigma. Shear stress can be written as sigma. For example, if it is sigma 1 2, sigma 2 3, seeing those abbreviations, you will understand that it is shear. In normal, it is 1 1 2 2 3 3. And tau, you can also write shear stress as tau. The tau 1 2, tau 2 1, tau 2 3, tau 3 2, like that. Here, one very important aspect is, if I write any stress component as sigma ij, what I is representing and what j is representing? What is the convention of writing a component? So as per the drawing, you can clearly understand I basically represents the plane on which the stress is acting, on which plane the stress is acting, plane. On the other hand, j represents the direction towards which stress is acting. So j is basically direction. For example, you can understand sigma 1 1. It is acting on plane number 1, that is the plane perpendicular to the direction 1, and it is acting along the direction towards the direction 1. So it is sigma 1 1 or sigma xx. Similarly, sigma 1 2 means it is acting on plane 1 and it is a shear stress and acting along the direction 2, and so on. So there are 3 normal stress and 3 independent shear stress. If you know any 3 shear stress, you can complete the stress tensor. And you know ij, sigma ij, here I represents plane on which stress is acting, j represents the direction towards which stress is acting. The same thing is drawn again in this diagram. The stress tensor is written here, sigma xx, tau xy, xz, and you know yx equal to xy. From moment balance, you know this is symmetrical. So stress tensor is symmetrical tensor. This is very clear. Again, the same drawing is here as I have shown. Again, you can have a look. Normal stresses are indicated as red arrows. Shear stresses are indicated as blue arrows. And now the box or parallelepiped that I am drawing, I am giving it a number. The origin is at O, and I am writing is in some form that the top plane is AFDE, the side plane is sorry, ABC. Here I have to write something. You can take a particular, suppose a G or something value here. Yeah. So Y plane is basically FDGC, X plane is EBGD likewise. Now we are interested to know stress at a plane. What is the stress acting at any plane? We know the face planes, what are the stresses acting? But we are now interested to know, okay, I understand that on X plane, Y plane, Z plane, how stresses are acting. But if there is any arbitrary plane at any angle, any orientation, how to calculate the stress on that plane? So you see here inside that body, I have drawn a particular plane by red color, which is ABC. I have drawn a plane which is ABC. And I want to know what is the stress acting on the plane ABC and how to represent the stress on the ABC plane. So to define a particular plane, first thing that you need to know is what is the direction cosine for that plane. So here you see we are writing alpha 1, alpha 2, alpha 3 is the direction cosine for the ABC plane. What does that mean is if you draw the normal to the ABC plane, and if the normal of the ABC plane makes an angle theta 1 with direction 1, then alpha 1 is basically cos theta 1. Similarly, ABC plane normal is making an angle theta 2 with direction 2. So cos theta 2 is alpha 2. Similarly, cos theta 3 is alpha 3. So to define any plane inside a body, you need to know the direction cosines of that plane. How the plane normal is oriented with respect to the three major axes that you have, X, Y, Z, or 1, 2, 3 respectively. So we know its direction cosine is alpha 1, alpha 2, alpha 3. And I am also defining the area of the ABC plane is delta. Area of the ABC plane is delta. Now the stress that will act on ABC plane will actually be the resultant of the stresses that will act, because you know that you are basically applying stress at the origin at any arbitrary way. So how the body is subjected to that stress. So the stress at ABC plane will now depend on the stresses acting on the facial planes, face planes, which are basically it will be function of stresses acting on AOB plane, because the stress acting on those faces will contribute to the resultant stress on the inclined ABC plane that I am picking up. Then it will also depend on COB plane, and it will also depend on AOC plane. So the stresses acting on AOB like this, and like this. The stresses acting on OCB, that is something like this, and like this, and like this. And stresses acting on AOC, that is normal, is this, and shear is this. So that will ultimately contribute to the stresses on the ABC plane. So in the next picture, I am just showing how the stresses on the ABC plane, resultant stresses on the ABC plane can be represented. You can either represent the stress on ABC plane by two component. One is normal, net normal stress, which I am drawing in blue color at sigma n. It is acting along the plane normal direction, perpendicular to the ABC plane, and the resultant shear component, sigma t. So either you can represent the stress on ABC plane by the blue components, sigma n and sigma t. Even you can represent them in terms of the stresses, net stresses acting along particular major axis, sigma 1, sigma 2, and sigma 3, as indicated by the green arrows. So either you can represent them by normal and shear, as indicated by blue arrows, or you can even resolve in three components along three major axes. But whatever be there, all will be related. All are the components of the net stress that is acting. And net stress, suppose something like this. If I consider the net stress sigma that is acting on ABC plane, the resultant is something arbitrary, something like this way, something it is acting, and it will vary. So you can either divide it into normal shear component, or you can divide it into major axis way. The stress is acting along the major axis. The three norm perpendicular axis. Now here I am writing down on all these three planes, that is AOB, COB, and AOC, how the stress components are acting. On AOC plane, which is plane number 1, because it is perpendicular to the direction 1, normal stress is sigma 1, 1, shear stress is tau 1, 2, and tau 1, 3. Similarly, on AOB plane, which is the plane number 2, perpendicular to the direction 2, normal stress is sigma 2, 2, shear stress is sigma 2, 1, and sigma 2, 3. Similarly, OBC plane, that is the basal plane, which is plane number 3, normal stress is sigma 3, 3, shear stress is sigma 3, 1, tau 3, 1, and tau 3, 2. Yeah, these two are the shear stress. So these stress are actually acting on this entire structure, entire body. And we are interested to know the net stress acting on the ABC plane. So how to represent that? To represent that, I have to do the force balance. So suppose I want to derive the value of sigma 1 in terms of the stress tensor components, because these are the stress tensor components. And sigma 1 is the net stress acting on the ABC plane along direction 1. How they can be related? They can be related if we equate the total force acting in a particular direction. Because we know the net force in any particular direction is 0 for a body to be under static equilibrium of forces. So the force acting at a particular direction must balance each other. So you see sigma 1, 1 is acting in the positive one side, sigma 1 is acting in the positive direction of 1, and sigma 1, 1, sigma 2, 2, 2, 1, and sigma 3, 1 are acting in the opposite side. That's why we can balance them. So what is the, because these three values are basically the stresses acting along the direction 1. These three values are the stresses acting along the direction 1, the stress components that is acting along the direction 1. So how much force is contributed by sigma 1 stress? To know that, what we need to know is the area of AOC. What is the net area of AOC? What is the net area of AOC? We know the area of ABC inclined plane is delta. So what is the area of AOC? You may think, and you will find the answer to be delta alpha 1, because the direction cosine of ABC plane is alpha 1. So the perpendicular to the ABC plane is having a direction cosine with respect to axis number 1 is alpha 1, and the AOC plane that we are considering is basically plane number 1, perpendicular to the direction 1. So its area will be delta alpha 1. So we can write sigma 1 delta alpha 1. Similarly, tau 21 is acting on AOB plane, which is on the plane number 2. So the area of plane number 2 will be how much? If the area of ABC is delta, it will be delta alpha 2. The area of plane number 2 will be delta alpha 2. So you multiply that area to find the force contributed by tau 21 shear stress. Similarly, the area of plane number 3, that is OCB or OBC, is delta alpha 3. Delta alpha 3. As we say, delta is the area of ABC plane, which is having alpha 1, alpha 2, alpha 3 direction cosines. So the net force contributed by the shear stress tau 31 is tau 31 delta alpha 3. So these three will be counterbalanced by the net stress acting on ABC plane along direction 1, which is sigma 1 delta. Sigma 1 delta is the net stress acting on ABC plane along direction 1. So the stresses acting on the three facial planes will actually contribute to the resultant stress acting on the inclined slanted plane, as I said. Now, if I write sigma 1 in terms of the normal stress and shear stress that is acting on the ABC plane, the normal stress sigma n and shear stress sigma t that is acting on ABC plane, you will find alpha 1 will be contributed by a component of the normal stress, which is sigma n alpha 1. So sigma 1 contribution will come from sigma n, area of that plane is delta. Sigma n alpha 1 will be the contribution of sigma n towards delta 1, towards gamma 1, sorry, towards sigma 1. Similarly, sigma t will also have a contribution towards sigma 1. This is sigma t. So if I consider the angle between the sigma t and sigma 1 is phi, so sigma t will have a contribution of sigma t some cos phi. And we know alpha 1 is basically cos theta 1, because the perpendicular direction is making angle, say theta 1 with the sigma 1 direction, the major direction, and its direction cosine is alpha 1. So sigma n alpha 1 will be the contribution of normal stress towards sigma 1, and sigma t, some cos, some angle, will be the contribution of shear stress on sigma 1 stress. So this makes the force balance along the direction 1. This makes the force balance along the direction 1. Similarly, you can understand there will be force balance along direction 2 and direction 3. So can you write them down in this way? I can try. I have to write, suppose direction 2. Along the direction 2, the balance will be something like, say, tau 1 2 delta alpha 1 plus sigma 2 2 delta alpha 2 plus tau 3 2 delta alpha 3 equals to sigma 2 delta equals to sigma n delta alpha 2 plus sigma t cos certain other angular value. The angle between sigma t and sigma 2. This particular angle. Similarly, if I write down the force balance along direction 3, sigma 1 3 delta alpha 1 or tau 1 3 delta alpha 1 plus tau 2 3 delta alpha 2 or tau 3 2 2 3, right, plus sigma 3 3 delta alpha 3 equal to sigma 3 delta equal to sigma n delta alpha 3 plus sigma t cos another angle that sigma t makes with direction 3. So this will be the 3 equations. These will be the 3 equations. Now we have a important consideration. You have the generalized form already defined. Now we have an important consideration that there is a term called principal stress. Something called principal stress. What is principal stress? Because it is very important in terms of mechanics or balance of stresses. Principal stress is defined as the normal stress acting on a plane where there is no shear stress. Normal stress acting on a plane where there is no shear stress. For example, I am considering a plane, any arbitrary plane. The entire stress that is acting is the normal stress. So basically, sigma, the entire stress that is acting is sigma n. And there is no sigma t, there is no shear stress. So sigma t equal to 0. So on the principal plane, this is called principal plane, the stress that is acting is fully normal stress and there is no shear stress. Very important consideration. For example, when we do a tension test, suppose I consider an uniaxial tension test. This is my specimen. I apply a load in this direction, I apply a load in this direction. What is this particular plane, the cross-section plane? Is there any shear stress on the cross-sectional plane? The answer is no. There is no shear stress because the entire load is leading to normal stress on the cross-sectional plane. So that is one of my principal plane on which there is no shear stress. Similarly, the perpendicular planes, there may not be any normal stress value on them, but there is no shear stress either. So I have to write those planes also as principal plane because there is no shear stress. And there is a normal stress, and the value of normal stress equal to 0. So here I will write there is one normal stress on the perpendicular cross-sectional plane that I write as principal stress in Roman. Principal stress is written in Roman, sigma Roman 1. Sigma numerical 1 is stress acting along, net stress acting along direction 1. Sigma 1 is the stress tensor component acting on plane 1 along the direction 1. So in uniaxial tensile loading, there is one principal stress, sigma Roman 1, and there are two other principal stress acting on the longitudinal planes. If you take two longitudinal plane perpendicular, we write them as sigma 2 and sigma 3. Those are also principal planes on which there is no shear stress, and the normal stress on those planes are also 0. So principal plane is the plane on which there is no shear stress, and the entire stress is normal stress, and the normal stress value can be 0, can be positive, positive means tensile, can be negative, negative means compression. But the criteria has to be there is no shear stress. So if there is no shear stress, then what I can do? Then I can ignore this term. This term is 0 because shear stress is 0. Suppose my ABC plane is the principal plane. Suppose my ABC plane is the principal plane. Then there will not be any shear stress on that plane. So shear stress component I can write as 0. I can cross this. So only term that remains is the normal stress term, sigma n delta alpha 1. And one more correction I can do. I can write sigma n as sigma. Sigma is basically the net stress that is acting on the plane number ABC. So the net resultant is ABC, and if there is no shear stress, the net resultant will be the same as the normal stress. Since in generalized case, I had a shear stress, I had a normal stress on that plane, so I have shown the net resultant in a different way so that you can divide it into normal component and shear component. But if there is no shear component, then the net stress will be basically your normal stress. So you can write sigma n, or the net stress that is acting sigma is basically the same, and that is acting perpendicularly. So the expression can be simplified for principal stress as sigma 1 delta alpha 1 plus tau 2 delta alpha 2 plus tau 3 delta alpha 3 equal to sigma delta alpha 1. What I can do? From that, I can cancel the delta values. And since sigma n alpha 1 is now sigma alpha 1, what I can do is now I can bring it to this side. So this term will now become sigma 1 minus sigma alpha 1. This term will now become this sigma 1 minus sigma alpha 1 plus tau 2 alpha 2 plus tau 3 alpha 3. And since this has come on that side, this will become 0. So that is my final expression considering force balance along direction 1 for principal plane, where sigma is the principal stress acting on the principal plane ABC. Similarly, for direction 2, what will be my expression? My expression will be something like sigma 1 2 alpha 1 plus sigma 2 2 or tau 1 2 alpha 1 plus sigma 2 2 minus sigma alpha 2 plus tau 3 2 alpha 3 equal to 0. And the final expression will be tau 1 3 alpha 1 plus tau 2 3 alpha 2 plus sigma 3 3 minus sigma alpha 3 equals to 0. So I can have 3 expressions and I have to find the solution to that. So I will show you the other things later. Again, coming back to the same configuration, that I am interested to know the net stress on ABC plane. In my PowerPoint, everything is nicely written. ABC plane, and the net stress on ABC plane will be determined by the stresses acting on, say, this point is considered as P. So APB plane, BPC plane, and APC plane, and the stresses are shown. ABC has area delta, APC has area delta alpha 1, APB has area delta alpha 2, BPC has area delta alpha 3. Direction cosine of that inclined ABC plane is alpha 1, alpha 2, alpha 3, body under static equilibrium. So stress along in the direction 1, as I said, sigma 1 delta equal to sigma 1 1 delta alpha 1. You can see the balance is done along direction 1, direction 2, direction 3, and now we are considering here, we are considering the plane to be principal plane, not taking the sigma t terms. So straight away I can write it as sigma alpha 1. Sigma 1 I can write as sigma alpha 1 because sigma equal to sigma n, normal stress. Similarly, sigma 2 I can write at sigma alpha 2. Similarly, sigma 3 I can write at sigma alpha 3. Taking it to the other side, you can find the 3 expressions are now set for principal planes. Now these 3 expressions to be valid, I want to find the solution. I want to determine 3 values of sigma for which this solution can be achieved. There can be 3 possible values of sigma. And basically the stress tensor, though I am writing in terms of component sigma 1 1 1 2 1 3, actually these will be real values. How much stress is acting along direction 1 in a body can be written as sigma 1 1 equal to 300 MPa, sigma 2 1 equal to sigma 1 2 equal to 140 MPa, sigma 3 1 equal to sigma 1 3 equal to 40 MPa, sigma 2 2 equal to minus 100 MPa, that is compression of minus 100, sigma 3 3 equal to 0, there is no stress, suppose. So basically the stress tensor components are real stress values. When we will give a stress tensor to you for further derivation, we will give them in the form of a tensor having values. Say each component having a particular value of MPa. So when on the bridge some truck is moving and it is applying a stress in the z direction, say I say sigma zz can be derived from the weight of the truck divided by the area. Similarly, wind is blowing in the transverse direction, say direction 2, then the wind velocity and the wind force will determine the stress sigma 2. So these will be real values, and based on those real values, I want to derive the principal stress. Because I can derive principal stress, then further mathematics will be easier to deal with. So so this determinant becomes 0. Sigma 1 1 minus sigma, sigma 2 1, sigma 3 1, sigma 1 2 2 2 minus sigma 3 2 1 3 2 3 3 3 minus sigma 2 0. For the 3 expression to be satisfied, this determinant has to be 0. Now you have to expand them. In the next slide, these are expanded. So if you expand, you will find this third order expression, sigma cube plus a sigma square plus b sigma plus c equal to 0 form. You will get it, where a is represented by the component values 1 1 plus 2 2 plus 3 3. B is represented by the more component values 1 1 into 2 2, 2 2 into 3 3, 1 1 3 3, 1 2 square, 2 3 square, minus 1 3 square. So this is the B. And this is C, 1 1 2 2 3 3, like that. This is C. And remember, A, B, C, these coefficients, basically these are coefficients, and these are called invariants. Remember, these are called invariants, stress invariants. Why these are called invariants? Because those are independent of your selection of your coordinate. Whatever way you choose your coordinate 1, 2, and 3 or x, y, z. In our case, we have classically determined as 3 major axes of the parallelepiped. It may not be. It may be 3 other mutually perpendicular directions. But whatever you consider, way you consider your coordinate, more specifically Cartesian coordinate, you will find ABC values will be the same. That's why they are called invariant, independent of coordinate system. Now, if someone solve these 3 expression, 3 solution can be obtained. And these 3 solutions are written as sigma Roman 1, sigma Roman 2, and sigma Roman 3, where sigma Roman 1 is greater than sigma Roman 2 is greater than sigma Roman 3. They can also be equal. All 3 can be equal. All 3 can be different. Any 2 can be equal. But the way we represent them the highest value as Roman 1, the second highest value as Roman 2, and the third highest value as Roman 3. This is the convention. So if I ask you, what are the principal stresses in uniaxial tensile loading? The answer would be sigma 1 will have some value that you apply. Sigma 2 equal to sigma 3 equal to 0. Thus, yes, you
Sir,
want to say
are
something?
all the real values? Sir,
Yes,
since it is
all are real values. All are real values. They are basically the functions of these components. As sigma 1 1, sigma 2 2, sigma 3 3, These are real values, I said, stress tensor
So
values.
on solving sigma, sir, it will give real value. Since it is cubic equations, the three real value, or it can be is that one real value and two complex like that.
This part immediately I cannot say. Okay, immediately I cannot say. But I will get back. I also don't remember. So I will also think and discuss with the TAs and get back. But suppose ABC is real, do you think that these will be complex values can be there? Suppose sigma cube equal to 15 sigma square plus 10 sigma plus 5 equal to 0. I don't remember sigma q equal to this set that values can also be negative. But if ABC are real values, then will the solution be complex? I don't remember. You also check, I will also check. Okay.
Okay, sir.
Yes. So suppose three of my principal stresses are 100 MPa, minus 30 MPa and minus 50 MPa. How to choose them? The selection would be sigma 1 equal to 100 MPa, sigma 2 equal to minus 30 MPa, and sigma 3 equal to minus 50 MPa. So more negative value will be sigma 3, intermediate will be sigma 2, and the maximum is sigma 1. Here you please be very, very careful. Sigma 1, sigma 2, sigma 3 are the three principal stresses, but their nomenclature depends on their absolute values. So that aspect is variable. So if it happens that you apply another tension in the major direction of sigma 2 and you increase it to 130, then like Air Force One where president lies, US president flies. So like sigma 2 will become now sigma 1, sigma 1 will to become sigma 2, and sigma 3 will remain as sigma 3. Okay. So remember the story of the movie of Air Force One. So whichever plane president lies, that is the Air Force One. So that is wherever the value is highest, that is sigma Roman 1. Wherever the value is lowest, that is Roman 3. And intermediate is 2. So don't stick to this 1, 2, 3 very strongly. Have your thinking flexible. Minus means compression, plus means tension. Now, what is the beauty of this principal stress? Whatever be the loading in a body, as you can represent in terms of 9 stress components of the stress tensor, which contains 6 independent values. Similarly, in every body, there will be 3 mutually perpendicular principal planes having 3 principal stresses. So for any way of loading, you can even find what are your principal stresses are. For example, in your tension, your applied stress is sigma 1, and the 2 perpendicular direction, if you are applying stress in z direction, that is sigma z is basically sigma 1, and the 2 other are 0. Similarly, in torsion, you rotate the specimen in 2 opposite direction. So there we write sigma 1 equal to minus sigma 3 and sigma 2 equal to 0. So any kind of loading can be represented by a stress tensor, and from the stress tensor you can calculate 3 principal stress values. So it is easier to represent the loading inside on the body. If you can represent the planes, principal planes with principal stresses, it is even easier because 3 values will be sufficient to explain the loading. If it is 100, 0, 0, you know it is uniaxial tension. If it is 100, 100, 0, you know it is What? If it is 100, 100, 0, what is the kind of loading? Biaxial, right? Biaxial. We call it balanced biaxial because 100, 100 is equal. Balanced biaxial loading. 150, 0 biaxial loading. 180, 50 triaxial loading. 100 minus 30 minus 50 is also triaxial loading. So by these three values, you can basically understand that how the principal stresses are acting on that particular body. So you will understand what kind of loading is that. So this is the beauty of converting the stress component into three principal stresses. Okay. So let me go back quickly again to my canvas screen, because I remember that I have made one more nice drawing for you. Don't know whether you will find it or not. Yes. So just to show you, if you see the black lines with the black arrows indicate the stress tensor components on the body. And inside this parallelepiped, you can draw another inclined parallelepiped where the face planes are basically three sets of principal planes, where red lines with the red parallelepiped is basically your principal planes with principal stresses, sigma 1, sigma 2, sigma 3. And on those facial planes, there is no shear stress, because you know principal plane contains only normal stress with no shear stress. So you can also represent the loading in the form of principal stress tensor. So principal stress tensor has only normal components, sigma Roman 1, sigma Roman 2, sigma Roman 3, with all the other shear components equal to 0. Here I am showing uniaxial tension where your sigma 1 is there, but sigma 2 and sigma 3 are also there. These are also principal, because on those axial planes there is no shear stress. So these are all principal plane, but these values are also 0. There is no principal stress value either. Principal stress is there, but the principal stress is 0. So we have to consider 0 value. Similarly, as I said, torsion, we apply one rotation. It is called pure shear loading. The entire loading is shear. So here, these are my, with respect to my radial planes, with respect to my, if I consider the radial planes, so I find there are two major principal components, that is sigma 1 and sigma 3, Roman 1 and Roman 3. These are the principal. And sigma Roman 1 equal to minus, because they are acting opposite. And this is your sigma 2, which is equal to 0, because you are not pulling the specimen. So this is your 0. So this is torsional loading. Let me go back again to my PowerPoint presentation. And if you quickly see Ditter's book, there is some kind of loading. I will also discuss it afterwards. There is some kind of loading which is called plane stress loading. Plane stress means, suppose a thin sheet is loaded along the plane of the sheet. You are applying stretching in two direction or two major direction. So that is called plane stress, or even shear, but on that plane. There is no stress along the perpendicular direction to the plane. So if you consider a plane XY, There is no stress along the direction of third direction. So that calculation you can do to simplify the problem, because the stress tensor will now become simpler. What you do? You cancel out all the stresses that are acting along third direction. So you will end up with 4 stress components: sigma 11, sigma 12, sigma 21, and sigma 22. 4 stress component you will end up with. And here in Dieter's book, you will see direction 1 is shown, direction 2 is shown. This inclined line is showing a plane, which is considered as principal plane. And on that plane, sigma equal to sigma n. The net stress on that plane is basically the normal stress. And that's why that is my principal plane. So if you consider only 4 components, the derivation becomes even easier, because now your determinant, principal stress determinant, what will be? Sigma 11 minus sigma 21, sigma 12, you know sigma 21 and sigma 12 are same, sigma 22 minus sigma equal to 0. Previously there was 3 expressions, through a 3 order determinant equal to 0. Now 2 equations you have to satisfy, so determinant is 2 order equal to 0. Here you see sigma 1 equal to sigma cos theta, that is sigma alpha 1, cos theta is alpha 1. Similarly, sigma 2 equal to sigma cos theta 90 degree minus theta sin theta equal to sigma alpha 2. You can clearly understand. So if you expand this expression now, you will get a square equation: sigma square minus sigma 11 plus sigma 22 sigma plus sigma 11 sigma 22 minus sigma 21 square. 2 1 1 2 are the same, so square up equal to 0. So you can, if I give you value of sigma 11, sigma 22 and sigma 21, you can clearly determine the value of these coefficients and get the expression of sigma Roman 1 and sigma Roman 2 by applying Sridharacharya's formula. Sigma Roman 1 equal to sigma 11 plus sigma 22 by 2 plus under root sigma 11 minus sigma 22 by 2 square plus tau 12 square under root. Similarly, you will find there will be only one more principal stress in this case, because third principal stress we are not considering, since it is a biaxial loading, equal to sigma 11 plus sigma 22 by 2. In place of plus, it will be minus, because the final expression will be plus minus. So plus value will be higher value, sigma 1, minus value will be lower value, that is sigma 2. Sigma max and sigma min. So these two are the principal stress values that you will get. And as I said, a little going out of the what we have derived, let me finish that. Now, there is one more interesting aspect, is what is the maximum shear stress? Since we have considered principal planes where shear stress equal to 0, there will also be plane where shear stress value will be maximum. So that plane is called the maximum shear stress plane. On which plane shear stress will be maximum? That also can be calculated by considering all the inclined planes where there are shear stress and taking derivative of sigma t by delta alpha 1, alpha 2 and alpha 3 equal to 0 to maximize the condition. And if you do this expression, you will find an interesting result, is the magnitude of the maximum shear stress value will be sigma 11 minus sigma 22 by 2 whole square plus tau 12 square under root. That means this part of the expression, the principal stress has 2 parts. The second part, sigma 11 minus sigma 22 by 2 square plus tau 12 square under root, that is the value of the maximum shear stress. So maximum shear stress thus can be represented by sigma Roman 1 minus sigma Roman 2 by 2. The difference between the principal stresses. The difference between the principal stress provides you the shear stress. This is a very important consideration. This is a very important consideration, and it can be also derived that maximum shear stress planes will be inclined 45 degree with respect to your principal planes or principal directions. Previously in class, I have told you that shear stress acts as 40 maximum shear stress plane acts at 45 degree with respect to your major applied loading direction. So if you apply an uniaxial tension, you have sigma 1 as applied force. 45 degree to that, you will find the maximum shear stress working. And that is why the shear lip that forms occurs at 45 degree angle, because metal tends to shear at 45 degree. Similarly, when fracture occurs under shear, that is 45 degree. Even the slip bands that form inside, if you do a loading of a single crystal, you will find that is 45 degree with respect to the loading direction, because maximum shear stress occurs at 45 degree angle. Sometime it may not be absolutely 45, but close to that. And second important thing I have mentioned is difference in principal stress gives you shear stress. For example, if three principal stresses are equal, sigma Roman 1 equal sigma Roman 2 equal sigma Roman 3, that state of stress is called hydrostatic state of stress. Hydrostatic state of stress. Similarly, if two are equal, one is unequal, it called cylindrical state of stress. If three values are unequal, then triaxial state of stress. But remember the hydrostatic stress state of stress. This is a very big significance. There is a big significance. In this slide, I am showing the principal planes as the face planes of the parallelepiped. The face planes of this box are the principal planes, and some of the principal directions, say sigma Roman 1 major direction is shown. So you will find there will be three possible set of maximum shear plane inclined at 45 degree with respect to the principal loading directions. Why I am saying all these things? Because come back to the canvas screen. So what I understand is, if I consider my these and these principal stress components, so these 45 will be my two sets of maximum shear plane. Similarly, if I consider these and these principal component, similarly, those who will be inclined 45 degree with respect to them, they will be actually some kind of 45 degree you have to draw with respect to these two. So that will be your maximum shear between them. Similarly, I can consider this principal and this principal. So whatever 45 you draw between them, that makes say, you have to just understand that orientation, something like this. This may be something like this. Something maybe like this and like this, 45. So you can understand there will be 6 such 45-degree plane that you can draw. 110 type of plane in a unit cell that you can draw. So depending on your loading, if you consider 1 and 3, there will be one maximum shear. If you consider 2 and 3, there will be one maximum shear between them. And 1 and 3, there will be one maximum shear between them. So there are 3 potential candidate of maximum shear stress, as I am writing here. Tau max 1, tau max 2, and tau max 3. Now 2 and 3 will depend on the value. What are the absolute values of sigma 2 and sigma 3 and sigma 1? That will decide who is 2 and who is 3. Sigma 1 minus sigma 2 can also be 2 if that difference is more than sigma 2 minus sigma 3. So if I give you 3 particular value, arbitrary value, you will be able to easily calculate. Suppose I give 100, 70 and 20. So you will understand who is the maximum, who is the second, and who is the third shear stress component. But there are 3 candidates for maximum shear stress. Out of that, these components will always be the maximum, 1 and 3. Because 1 we take as highest, 3 we take as lowest value. But there can be even 2 candidates. If sigma 2 equal to sigma 3, then 2 of them will be equal. So 2 of them will be considered as maximum. That's how. Now why I am saying so? Because I want to know when the plastic deformation will happen. A small but detectable plastic deformation will happen. And all this derivation I am doing considering based on a concept which is called continuum mechanics concept. Continuum mechanics. So dislocations and other things do not come into this. This is a mechanistic concept, pure mechanics, solid mechanics, continuum solid mechanics. No atomistic consideration is coming in these calculations. Simply metallurgical engineer know that, mechanical engineer know that, civil engineer know these derivations. So everybody has to use for their purpose. So there comes some of the contribution of some scientists. For example, Tresca. Tresca has come up with a very important derivation because people were interested to know when the yielding will occur. If I ask you when yielding occurs in an uniaxial tension, what would be the answer? When yielding will occur in an uniaxial tension, in a tension test, the answer is when maximum principal stress sigma 1, which is your applied stress, exceeds sigma naught. When sigma 1 exceeds sigma naught, that is the condition for yielding to occur. And what is sigma naught? Sigma naught is called, sorry, this is my tension condition. Sigma naught is called yield strength in uniaxial tension. Remember the terminology. Yield strength is not the same in every loading. if you apply tension, you have to apply higher stress to cause yielding than in torsion, because in torsion shear component is much more. In tension shear component is less. So in tension you have to apply more higher principal stress to get a sufficiently high resolved shear stress which will cause yielding. So yield strength is different. Yield strength in tension is higher than the yield strength in torsion. That is even higher than the yield strength under plane strain condition, where 3 principal stress values are there and 3 positive values are there. This is a very important consideration. Tresca said, for any, I give you any arbitrary principal stress tensor. Even I can give you simple stress tensor, sigma ij, because from stress tensor, you can calculate the principal stress values. At least you have seen how the stress tensor components are related to the principal stress values for biaxial loading condition. Similarly, if you do a more rigorous mathematics, you can derive the values for triaxial loading also. So if I give you simply sigma ij stress tensor, you can derive the principal stress tensor. If you know the principal stress tensor, you can calculate the maximum shear stress that is acting. And Tresca said yielding will occur when maximum shear stress exceeds the critical value. And that critical constant value is represented by the letter K. It is represented by the letter K. So maximum principal stress, which is sigma 1 minus sigma 2 by 2, it has to exceed. Criticality is equal, and just crossing that point is exceed. So when that will occur, then yielding will occur. Now I will calculate what is the value of K. So this condition that Tresca has derived is based on the stress tensor and principal stress tensor. So it is applicable to any form of loading, tension, compression, bending, torsion, whatever loading you see, that can be represented by a stress tensor, which can be converted to a principal stress tensor, 3 principal stress values. So from that you can derive the maximum stress. So it is applicable to any loading, means it is also applicable equally to the most simple form of loading. And what is the most simple form of loading? The most simple form of loading is uniaxial tensile loading. It is applicable to uniaxial tensile loading. It is applicable to torsion loading as well. It is applicable to any general loading that a bridge or a railway line or even our human body suffers when we walk, when we stand in one place. So converting this expression, we can write sigma 1 minus sigma 3 by 2 should be greater than or equal to K. Apply the most simplest loading condition, uniaxial tension. When yielding occurs under uniaxial tension, when sigma 1 exceeds sigma naught. So in place of sigma 1, if you write sigma naught, you know in tension sigma 3 is 0. You cross this term. So what is the value of K that you get? Value of K is a constant, and the value of K is sigma naught by 2. Now again come back to the generalized expression, and the generalized expression of Tresca's criteria is sigma principal, sigma Roman 1 minus sigma Roman 3 has to be equal and exceed of sigma naught. And what is your sigma naught? Sigma naught is your yield strength in uniaxial tension. So when you do a tension test, you get the absolute value of sigma naught. So now if you know the value of sigma naught, you can calculate that how much maximum shear stress a particular bridge can be when it is under complex loading condition, and you can design accordingly. So it is very important to understand that all the body does not yield at a particular yield strength. It depends on the loading. As I told before, that if you take a thin specimen, it will be under uniaxial tension. But if you take a big, very thick specimen, it will be triaxial. So when it is triaxial, then sigma 2 and sigma 3 is coming. So then situation will be different. You need to apply higher sigma 1 to get this kind of criteria satisfied. So the generalized expression is sigma 1 minus sigma 3 has to be exceed sigma naught. For example, suppose in your, your yield strength of your body is 300 MPa. Uniaxial yield stress, uniaxial yielding when you do. So when sigma, your maximum principal stress, which is the applied stress, exceeds this value, yielding will occur. But I am considering another simple problem. Suppose I apply a sigma 3 in positive direction with a value of 100 MPa. What will happen? Suppose in this direction, I am additionally applying a stress of 100 MPa. Then what sigma 1 you need to reach to cause yielding? 300 minus sigma 1 minus 100 should exceed 300. So sigma 1 now increases to 400 MPa. So simply if you introduce one more stress, sigma 3 or sigma 2, 200 or sigma 3, 300, you will find your applied stress need to increase to cause yielding. And why it is happening? Because when you are deforming a body, for yielding to occur, it has to increase its length, and to increase its length, it has to contract in the other two directions. So if you simply apply one principal stress along applied direction, that contraction is free. But if you apply another tensile stress along these directions, will the contraction be easy? Will this contraction be easy? You are basically opposing the contraction by applying this tension. So you need to apply even higher applied stress to lead to this contraction against these forces and get the body deformed. So this is the basic theme of this problem. And one more very important value, suppose I consider uniaxial yield strength is 300 MPa. I am applying on a body three principal stresses in three principal perpendicular direction in a simple tension specimen. Suppose a tension specimen, three perpendicular direction, I am applying stresses 1000, 1000, 1000. Will the yielding occur? Answer is no. The yielding will not occur. Because there is no difference between the principal stress. So as I said, the difference between principal stress is necessary for shear stress. If there is no difference in principal stress, then that loading is called hydrostatic loading condition. When we stand in free air, we are under hydrostatic pressure from all sides, which balance us. And that's why we do not fall down or our skin do not get distorted. Because there is no shear on us. We are under equal pressure from all sides. But we can fall down when? If there is a heavy wind from one direction. So in that side, more pressure is coming compared to the other sides. So that is creating a shear kind of a stress and we are falling down. That is creating a difference. Similarly, if I give you a knock on your face, you may fall down because from that side, a higher stress is coming compared to the other side's balance. So this difference actually leads to changes, deformations. And hydrostatic type of stress leads to only volume change. If it's a compression, then there will not be any, if there is a hydrostatic compression, we are also under hydrostatic compression with a very heavy force from all sides. Several elephant forces are acting on our right, left, top and front and below, back. But we are fine because the principal stresses are balanced. There is no difference. But whenever there is a difference, there will be a change. If one side a vacuum is created, we will immediately fall in this side, in that side. So there is a need for difference in principal stresses for plastic deformation to occur, for permanent change to occur. Otherwise, if there is hydrostatic compression, very small amount of elastic shrinkage will occur. So our volume will reduce. If there is a hydrostatic tension from all sides, if you enter vacuum, all sides there may be a stretch. So or internal pressure is pushing you. So there may be a little bit of expansion. So hydrostatic stress leads to volume change and difference in principal stress leads to permanent changes. Shape change, permanent shape change. Coming back to the presentation, 3 sets of maximum shear stress planes with respect to the principal planes are shown nicely, 45 degree. Tresca's criteria is written. I have not talked about the torsion. We know the generalized expression in Tresca is sigma 1 minus sigma 3 greater than or equal to sigma naught. What is the loading in case of torsion? In case of torsion, we know yielding occurs when sigma 1 equal to minus sigma 3 and they exceed tau naught. What is tau naught? Tau naught is the yield strength in case of torsion, which is pure shear loading. So tau naught is called shearing yield strength. As sigma naught is called tensile yield strength, tau naught is called shearing yield strength. So following Tresca's criteria, what is the relation? So in place of sigma 1, we have to apply tau naught, and sigma 3 will become minus tau naught. So 2 tau naught should be greater than or equal to sigma naught. So critical condition is, we can write as the expression, the relation between shearing yield strength tau naught and tensile yield strength sigma naught as sigma naught equal to 2 tau naught. So if you apply torsion, yielding will occur at 150 MPa when your tensile yield strength is 300 MPa. So in Tresca's criteria, relation between tensile yield strength and torsional yield strength is sigma naught equal to 2 tau naught. I am nearing to the end. Principal stress tensor now can therefore be divided into two components, two parts. Sigma 1, sigma 2, sigma 3, 0, 0, 0, 0. This is the principal stress tensor. If I subtract hydrostatic stress tensor is also all the major normal stresses are equal. So I can take out the hydrostatic part from the principal stress tensor. What is hydrostatic component? Sigma 1 plus sigma 2 plus sigma 3 by 3. This average principal stress is considered as hydrostatic stress. Average of principal stresses is called hydrostatic stress. So I take hydrostatic stress tensor. I basically subtract principal stress tensor minus hydrostatic stress tensor. So the first term, sigma 1 minus sigma 1 plus sigma 2 plus sigma 3 by 3. So what will be the value? Sigma 1 minus sigma h. This is called the stress deviated tensor. So 2 sigma 1 minus sigma 2 minus sigma 3 by 3. So the first term will be 2 sigma 1 minus sigma 2 minus sigma 3 by 3. You can write it as within bracket sigma 1 minus sigma 2 plus sigma 1 minus sigma 3 by 3. Similarly, this term you can write it as sigma 2 minus sigma 3 plus sigma 2 minus sigma 1 by 3. Similarly, this term you can write. So you can see every term in this is basically again coming back to the difference in principal stress. So when we subtract the hydrostatic stress tensor, the remaining tensor values again comprise of the difference in principal stress terms. And difference in principal stress we know represents shear stress. So hydrostatic stress tensor is not responsible for any plastic deformation. It only causes volume change. It only causes volume change. Stress deviated tensor is actually responsible for your plastic deformation. And that's why people consider, if I give you principal stress tensor, sometime we need to consider the stress deviated tensor, because actually that part is leading to plastic deformation. Now von Mises have done some more derivations, and what he has tried to say is, okay, I have derived stress deviated tensor and I consider it as a stress tensor, and I will try to calculate the principal stresses with respect to these stress deviated tensor. That means just considering that as an independent stress tensor, I will calculate the principal components of that tensor. Not necessarily to remember all those things, but you must understand the basics of the most important equations that is coming. So von Mises said yielding occurs when second invariant of stress deviated tensor exceeds the critical value. Like Tresca said, yielding will occur when maximum shear stress exceeds the critical value. Von Mises said, I will determine the stress deviated tensor. I will try to represent it again in the form of principal stress tensor. So that's why again he is writing it in the form of sigma minus first term, 0, 0, 0, sigma minus second term, 0, 0, 0, sigma minus third term. So this stress deviated tensor he wants to represent in terms of a sigma cube plus a sigma square plus b sigma plus c equal to 0 kind of an expression. And second invariant, that means b. First invariant is a, second invariant is b. Out of that expression, he is picking up the second invariant. This is not a part of this course, but it is important to understand that in the Ditter's book, it is written that Von Mises criteria said second invariant has to exceed a critical value. So what is the second invariant? Second invariant is in the form of this. You can write in the form of stress components 1/6 sigma 1 minus sigma 2 square plus sigma 2 minus sigma 3 square plus sigma 3 minus sigma 1 square plus 6 tau 1 2 square tau 1 3 square. Simply stress tensor components you can also write that second invariant. This is the invariant reaction I am showing. Sigma dash principle in this case is considered as dash. It is as it is the principle of stress deviator. If you write in terms of principal stresses, we have derived before 1/6 sigma 1 minus sigma 2 square plus sigma 2 minus sigma 3 square plus sigma 3 minus sigma 1 square. Remember this term, we are going to use it. I'm again going back to the canvas screen for the last time. I have to come to my next derivation, which is this. Von Mises said when this expression, second invariant of stress deviator component, exceeds a critical value, which is a constant, and this expression is a generalized expression applicable to any type of loading, whether you apply tension, torsion, bending, shear, whatever and whatever, so whatever complex, all will come under this general expression. So if it is applicable to all general expression, it is also applicable to simple tensile loading, uniaxial tension. And we know in uniaxial tension when yielding occurs, uniaxial tension yielding will occur when your applied maximum principle sigma 1 exceeds sigma naught and your tau sigma 2 and sigma 3 are equal to 0. Apply this in this expression. You will get the value of K. And what is the value of K you will get? K equal to sigma naught square by 3. So in place of K, write that sigma naught square by 3. What expression you will get? A very interesting and important expression that you will get is this expression. 1 by root 2 sigma Roman 1 minus Roman 2 square plus Roman 2 minus Roman 3 square minus Roman 1 minus Roman 3 square. Under root, these has to exceed sigma naught. And what is sigma naught? Yield strength under uniaxial tension. Yield strength under uniaxial tension. Why we are expressing these in terms of sigma naught? Because it is very easy to calculate from your tension test. And all standard actually represent tension test results, yield strength values under tension. So this value for every material is easily available. So if you apply a certain kind of whatever complex loading, 500, 300, 200, 200, minus 100, 0, you can tell, if I give you 3 principal stress values, you can tell whether yielding will occur or whether yielding will not occur, provided you know the yield strength value for uniaxial tension. In von Mises, what is the relation between yield strength in uniaxial tension and yield strength in pure shear, that is torsion? We know yielding will occur in torsion when sigma 1 equal to minus sigma 3 and both of them exceed shearing yield strength tau naught and sigma 2 equal to 0. So apply this in the von Mises criteria, keep sigma naught this side, you will get a relation between tau naught and sigma naught following von Mises, and tau naught equal to sigma naught by root 3 according to von Mises. But according to Tresca, tau naught equal to sigma naught by 2. So there is a difference. So now you may ask me, teacher, you give me a tensor, principal stress value, suppose I give. How can I say when yielding will occur? First of all, you have to check whether your principal stresses are satisfying the yield criteria. There are two yield criteria. One is Tresca's criteria and another is von Mises criteria. So Tresca I have shown before, von Mises I am writing here. So von Mises criteria. Now these are basically predictive criteria. So don't think that a criteria is satisfying means it will certainly happen, because a lot of other condition, materialistic condition, microstructure and other things will play a role, and these doesn't consider those atomistic or microstructural or nanostructural conditions. This is simply continuum solid mechanics. But for design this is quite applicable, because this gives you reliable prediction. It may not be very accurate, but it will be close. If criteria is satisfied, then you may say there is a high chance that yielding will occur, because Tresca and von Mises both are satisfied. Now among Tresca and von Mises, you see both of them have considered something, and there is a difference in their approach. So there is a difference in the values that we get. Whom to rely more? Who is more accurate? The answer is von Mises is more accurate, because von Mises also considers sigma 2. Von Mises considers all the three principal components, whereas Tresca considered only sigma 1 and sigma 3. So Tresca is less accurate, von Mises is more accurate. But Tresca also has a good thing, that Tresca is very simple. You need not have to do any mathematics, just verbally by thinking you can tell the answer. So Tresca is simplicity is the power of Tresca criteria, whereas better accuracy is the power of von Mises criteria. And these are predictive criteria that apply well for design, because if you know when, at what value, at what condition there is a chance of yielding plastic deformation of my bridge, I want to avoid the plastic deformation of my bridge. So first slide I have shown therefore a bridge and how different types of load applies on the bridge. So we don't want the bridge to sag down to end up in the river. We don't want that. So for any adverse condition, you have to be ready. If there is a strong wind, applies a compression sigma 2. If there is some earthquake, then what can be the maximum load it can take? And there we have to apply, consider the yield strength of the material, calculate sigma 1 considering adverse condition, and then what we do, we apply a safety factor, and a big safety factor we apply. If I get sigma 1 say 500 MPa, then I will apply a safety factor of 2 or even 3. If I apply a safety factor of 3, it comes down to say 170 MPa. So I will say when there is a strong wind, do not send any vehicle which is weight more than 170 MPa pressure. So I may restrict train moving at that time on the bridge, or I may restrict heavy truck on the time of bridge when there is a thunderstorm. So this is the beauty, and there that prediction from von Mises and Tresca are so helpful. So today long lecture on stress. Tomorrow I will record the lecture on strain. Thank you to the TAs and those who have joined, 4 or 5 people who are there. Okay, so let the recording be stopped.